We want to find the mass of a lamina bounded by y equals 2 times the square root of x, x equals 9, and y equals 0 with the given density function here. So the lamina would be bounded by these three equations here in the xy plane. We'll notice how this top curve is y equals 2 times the square root of x. This horizontal line is y equals 0, and this vertical line is x equals 9. Let's also determine the coordinates of the corner points here. We have the origin, which would be 0, 0. Here we have the point 9, 0. Here we have the point 9, 6. This is a fairly straightforward question because if rho of x, y is a continuous density function of a lamina in the plane region R, then the mass of the lamina is equal to the double integral over the region R of the density function. So in this case, we have the mass m is equal to the double integral. The integrand function is going to be sigma of x, y, which is x plus 1. Now for differential a, we'll have either dx dy or dy dx, and we'll set up both of the double integrals for this example. Let's begin with dx dy, meaning we integrate with respect to x first, then with respect to y. If we integrate with respect to x first, we need to determine the limits of integration for x by determining how this area is bounded to the left and to the right. We'll notice how the left is bounded by this curve given by y equals 2 times the square root of x, and to the right, it's bounded by x equals 9. But we need to solve y equals 2 times the square root of x for x if we want limits of integration for x. So starting with y equals 2 times the square root of x, we would divide both sides by 2, giving us the square root of x equals y divided by 2, and then we'd square both sides of the equation, giving us x equals y squared divided by 4. So y squared divided by 4 would be the lower limit of integration with respect to x. And then to the right, again, it's bounded by x equals 9, so 9 is the upper limit of integration with respect to x. Now with respect to y, because we already have the area bounded to the left and right, for y we integrate from 0 all the way up to this high point where y equals 6. So limits of integration with respect to y would be from 0 to 6. Now let's also set this up using the other order of integration. So we have the mass would also be equal to the double integral of x plus 1, but now we'll integrate with respect to y first, then with respect to x. So because we integrate with respect to y first, we want to determine which functions bound this area on the bottom and on top. Notice how y equals 0 bounds the area on the bottom, and y equals 2 times the square root of x bounds the area on the top. Which means with respect to y, we integrate from 0 all the way to 2 times the square root of x. Now that the area is bounded on the bottom and on the top, we integrate with respect to x from 0 all the way out to x equals 9. So with respect to x, we integrate from 0 to 9. Let's go ahead and use this form of the double integral in order to determine the mass. When we integrate with respect to y, we treat x as a constant, and therefore the antiderivative with respect to y would just be x plus 1 times y. Again, we're treating x and 1 as a constant. And now we perform substitution for y. And because we're treating x plus y as a constant, we have the integral from 0 to 9 of the constant x plus 1 times, when y equals 2 square root x, we have 2 square root x. When y is 0, of course, we have 0. Let's go ahead and write this as the integral from 0 to 9 of, let's write square root of x as x to the 1/2. So we have 2x to the 1/2 times the quantity x plus 1 as the integrand function. Let's go and distribute here. This is x to the first. So we have the integral from 0 to 9 of, we'd have 2x to the 1/2 plus 1 is 3/2, so x to the 3/2 plus 2x to the 1/2. And now we integrate with respect to x. So we'd have 2 times x to the 3/2 plus 1, that's x to the 5/2. And then instead of dividing by 5/2, let's multiply by 2/5. And then plus 2 times x to the 1/2 plus 1 is 3/2. Instead of dividing by 3/2, let's multiply by 2/3. Let's go ahead and simplify. So here we have 4/5 times x to the 5/2 plus 4/3 x to the 3/2. So when x is 9, we have 4/5 times 9 to the 5/2 plus 4/3 times 9 to the 3/2 minus, notice when x is 0, both of these would be 0. So the exact mass would be 4/5 times 9 to the 5/2 plus 4/3 times 9 to the 3/2. Now we could factor this or change the form. Let's go and leave it in this form though and convert it to a decimal. So going to the calculator, notice how as a decimal the exact value is 230.4. Now because we're not given units though, we don't know if this is slugs or kilograms, but this would be the mass of the lamina over the region R with the given density function. I hope you found this helpful.